Continuing on with the particle in a ring, we solved previously for the Hamiltonian and then for the energies, so we're going to move on now to the wave functions. So we have our particle in a ring model system, which, as we said, we have a particle which has zero potential energy if the radius is fixed at this radius r, and the polar angle theta is fixed at pi over 2, aka perpendicular to the z-axis. And then we have and then it's 0 on this ring here, under which those two conditions are satisfied, and the potential is infinite otherwise. So the wave function can only be non-zero at points along this ring, thus giving us our particle in a ring model. So this gives us a wave function which is effectively one-dimensional because there's only one variable that we have in this three-dimensional wave function. So doing this, we can reduce the Laplacian in our Hamiltonian from the three-dimensional case to our Hamiltonian is just minus h bar squared over 2m radius squared times second derivative with respect to azimuthal angle phi. And the energies we solved for this look very similar to the particle in a box. We have h bar squared n squared over 8mr squared. So instead of having the L in the denominator for the particle in a box, our effective L of our particle in a ring here is 2 pi r. It's the circumference of this total circle there, and that's encapsulated in this h bar, because in the particle in a box you have h, and here we have h bar, which gives you that extra 2 pi factor for each r here we have in that r squared. So we previously looked at the wave function. We saw that the wave functions are complex exponentials. Psi n of phi is going to equal e to the in phi, a complex exponential as you go around the ring there. And these n's are integers which have values which look like 0, plus or minus 1, plus or minus 2, etc. Again, differing from particle in a box in that these integers can be negative as well, and thus there are two states at each energy once you go above the ground state. So we have our wave function there, but there's one more thing we need to be concerned about. We need to find the normalization constant such that we have the right probability density for the particle all the way around the ring. So to find what this normalization constant is, we do what we always do. We say that there is a 100% chance of finding the particle somewhere, and that is equal to psi star times psi, which is the probability density for finding the particle somewhere in the region. And then we integrate with respect to all of the variables over the total domain of the wave function. So in this case, the total space that the variable phi spans is 0 to 2 pi, because 2 pi gets you back to where you started. So we integrate from 0 to 2 pi of psi star psi. Okay, so we can plug in psi star and psi here. Integral 0 to 2 pi d phi. We have n e to the im phi star times n e to the im phi. Okay, then taking the complex conjugate here, we have a square root of minus 1 and I there, so we have to switch the sign on that. So we're going to get 1 equals, and we can also take this factor of n and that factor of n and pull them out. N squared integral 0 to 2 pi d phi. Then we have e to the minus in phi. Oh, sorry, these should be n's. Yep, e to the e to the minus in phi, e to the plus in phi. Okay, then you notice we have a number times its inverse. X to the n times x to the minus n is just 1. So these two end up canceling out to give us a total of 1 there. So then what we end up with is that 1 equals our factor of n squared times the integral from 0 to 2 pi of d phi. And that is just n squared times 2 pi, because the integral of d phi from 0 to 2 pi is just 2 pi. So then we solve algebraically for n. We divide both sides by 2 pi and take the square root. So we have n equals 1 over square root of 2 pi. Thus, our final wave functions, our psi n of phi, is just 1 over square root of 2 pi e to the I n phi. So what do we have here? At n equals 0, we have e to the I 0 phi. So for psi 0 of x, or psi 0 of phi, yeah, we don't have a wave function of x there. We have a wave function of phi. So I should probably make that phi. Okay, psi of phi equals 1 over square root of 2 pi e to the I n phi. Okay, so our psi 0 of phi is just going to be 1 over the square root of 2 pi. It's the same at all places in space. It doesn't vary as we go around the ring there. It's a constant function. Then we have psi 1 just being 1 over square root of 2 pi e to the I phi. So it varies once going around the circle. Then psi 2 varies twice. There's 2 periods of the function going around. Psi 3, 3 times, etc. And the only difference between the positive and the negative integers is you have either plus or minus in the exponent. And the effect of that is basically whether the particle is traveling around the ring this way or the other way. If we picked a specific orientation to this axis, you've got at every n above 0, or every n not equal to 0, you've got 2 states at the same energy, one in which the particle is traveling to the left, one in which it's traveling around to the right, or just in opposite senses, as we can see here. There's no right or left on a circle, but we got 2 wave functions where the particle is at the same energy but traveling in different directions here. And that's the result for our wave functions for our particle in a ring.